Hello everyone, welcome back. It's not very special. We start with Mark Cerezo from Los Alamos National Laboratory from USA. Now I will introduce you Mark Cerezo. Mark Cerezo is a Guatemalan physicist currently employed as the staff scientist at Los Alamos National Laboratory. Mark obtained his PhD at the University of La Plata in Buenos Aires, Argentina, where he was working on quantum information, condensing matter, and foundations of quantum mechanics. Currently, Marco work is aimed at understanding the capabilities and limitations of additional algorithms on near-term quantum computers. Here, he studied phenomena such as their encode, the effect of noise in quantum algorithms, and has proposed several algorithms for near-term application. Okay, Marco, thank you for your presentation. Nice to have you here. Okay, you have approximately 4 or 5 minutes, okay? And after that, we will have questions. Thank you again.
Perfect. Thank you very much, everyone, for being here. Thank you to the organizers. I'm going to try to do something. It's been a while. Há muito tempo que eu não falo português, mas eu quero agradecer aos organizadores por este convite. That's as much Portuguese as I'm going to talk. I'm not going to try to butcher the presentation by speaking Portuguese. But if you have any questions, feel free to interrupt me and at any point. And today I'm going to be talking about geometric quantum machine learning, which is kind of like this name that we've given to the idea of combining geometrical information with quantum machine learning, or the subtitle of the talk, How I Stopped Worrying and Learned to Love Representation Theory. So first of all, an outline of the talk. I'm going to be first introducing why we talk about geometry and symmetries in the context of machine learning and quantum machine learning. I know that people might not be familiar with what representation theory is and how to work with symmetries, so I'm going to try to give a very quick crash course on representation theory. After that, I'm going to introduce this thing that we call geometric quantum machine learning, and I'm going to show how it works in a given toy model to give you a flavor of why this is useful. Finally, I'm going to present some theoretical and numerical results that we've obtained, showcasing the power of this framework. So first, let's start setting the scene. First, I'm going to be working on supervised quantum machine learning, which is this sort of setting where I'm giving a data set, which is composed of the form of quantum states and their associated labels. I actually don't know if you can see my mouse, but you might be able to see this laser pointer. Yes. So I'm going to be given quantum states and some set of labels, and I'm not going to make any assumption about the quantum states at this point. So they might correspond to classical data that I've encoded into a quantum state and that I want to work with, or they might just be quantum states that are coming from some quantum mechanical process and hence are already living in a quantum computer. And the whole point here is that what we're usually trying to do is that we know that those labels are assigned by some underlying function f that takes data from the data domain and assigns a label. And our goal is to train a learning model, in this case, something that makes use of a quantum computer, to try to match the labels of this function, this unknown function. For us, we already know that the most important thing about quantum machine learning models is how we build them, or what people in the machine learning community call the inductive biases. And the inductive biases is nothing more than the choices and the information that we put into our model. So for instance, that might be the choice of the quantum neural network. How is my parameterized quantum circuit organized? What measurement I'm going to take? What's the cost or loss function that I'm going to be training on, and whatnot. And the main idea is that if I have models that don't have inductive biases, that are just models that are generic out of the box, then we can expect them to have issues such as parent plateaus and poor generalization and whatnot. And the idea is that there is no free lunch, right? We do not have one model that we expect is going to be able to solve any possible problem. So the more we restrict our model, the more information we put in it, the more we can expect it to be useful. And our idea is to try to take a closer look at the data, find geometric information, and put that into our model in form of inductive biases. So first of all, let's talk about symmetries in classical machine learning. And I'm going to make a very crazy claim here, which is that if I take the picture of a cat, and then I roto-translate the cat inside of the picture, this is still a cat. Now, you might choose to believe me or not, but what I'm saying here is that a picture of a cat still depicts a cat if we roto-translate it over the pixel grid, right? So in a way, this is pointing to something very fundamental, because the picture changed, right? It's not the same picture anymore. But still, if I were to fit this into a learning model, I want the label cat to still be invariant. So we say that the label is invariant under the roto translation group. And this is going to be very important. We care about label symmetries and not about data symmetries. I take my data, I do something to it, I get a completely different data point, right? And of course, spoiler alert, quantum data also has symmetries. So say that, we want to train a model that is going to produce labels that are invariant on the roto translations. How would we go about doing this, right? So one way in which we can try to do this is via data augmentation. I take my learning model, I give it a picture of a cat, and then, it's working well. But then I roto translate it, and I try to still get the same predictions. So I wanted to learn the invariance. I do this a bunch of times, but the problem is that I'm feeding it a bunch of data with the same model. So at some point, I'm going to have to increase the model's capacity for it to keep learning about all of this invariance. So one of the big problems of data augmentation is that it is very data and parameter inefficient. So I have to build larger models and feed them more data for them to learn this invariance, right? And not only that, even if the model learned the invariance over the training set, there is zero guarantee that it's not going to be able to, that it's going to be able to predict and generalize this invariance that it is learned. So, the issue is that we have no guarantees over new and unseen data points. So, of course, what we would like is to design models that are invariant, that produce labels that are invariant by design, so that I just give it whatever picture roto-translated, and it will always see it as the same image, right? So this is it. This is a simple idea, right? We just want to build models that produce invariant labels by design. So how do we go about doing this? So in classical machine learning, people have been working for this for the past maybe, 90 years. And it's led to this field, which is called geometric deep learning. And for people who want to learn more about this, I highly recommend this. I'm not going to say manuscript. It's a book it's an archive. It's highly recommended. And there's this also GitHub with a lot of papers that are talking about the field. So in geometric deep learning, the main idea is first, we want to recognize the importance of symmetries in data. And this idea of we have roto translations that we were previously seeing has been generalized to groups, right? How can we embed the information of symmetries and groups into our models? And this has been applied to a wide variety of domains with very big amounts of success, right? And of course, what we're saying here is that by restricting the search space of our model, by putting geometric priors in it, we're going to reduce its expressibility or its expressiveness. And we can see that this should somehow make it easier to train and probably improve generalization, right? Because the search space is now just restricted to the set of functions that respect the symmetries that we know need to be satisfied. So from here, let me just start saying that I talked about groups and symmetries, and maybe this is not obvious how these two things connect. So the first thing that I want to talk to you is that symmetries form groups. So first, we need to define what is a group. And I know that this might be very obvious for a lot of people, but I still want to give an introduction so that we're all with the same language. So first, let me consider a set of objects and an operation, which is just going to be this star here. And what I want to do is that this star is going to combine any two elements of the set to produce a third element in the set, right? So for instance, if my set is just images of cats, and I just apply some operation, which is a rotation, I get some rotated cat. Then I can produce another operation, I get another cat. And it's very easy to see that I could just get from the first to the latter by doing a rotation with this combination. So this is already starting to point that there's some structure in groups. First of all, groups are associative. It doesn't matter if I first rotate the cat by θ2 or by θ1, I'm going to get to the same point, right? Then there is some identity. For every group, there is an object such that I don't do anything. And all the groups have inverses. That means that there exists for every element on the group, another element in the group such that their composition gives me the identity. In the case of rotations, This would be, I take a cat, rotate by θ1, then rotate by minus θ1, get back to the same space. So this is it. This is all the definition of groups, and we can already start to see how symmetries are going to form a group, because it's very obvious that if I have an operation that preserves the label, the composition of those operations should also preserve the label, right? And this is the main idea of symmetries. So what is this thing that we call geometric quantum machine learning? So what we want to do is want to port the ideas from geometric deep learning to quantum machine learning, so that we can build a framework where we can create quantum learning models that encode the symmetries of the problem at hand. And again, despite the relative simplicity of this program, its practical implementation requires us to know about groups and representations, and most specifically, this field known representation theory. So for people that are interested in this and maybe don't have a lot of background, we wrote a tutorial that is by quantum machine learning practitioners for quantum machine learning practitioners, which is aimed at providing people the basic tools for representation theory and how to implement them in quantum machine learning. Because something that I found is that whenever I got representation theory during my undergrad very briefly, and I wanted to go out there and read, and textbooks are usually written from a mathematical perspective. So it can make it a little bit less accessible, which this tutorial should not replace those books. I still encourage people to go and read, the well-written, properly mathematical formal books on representation theory, but this can give you an introduction. So it's this idea that groups encode abstract symmetries, and representations describe how those symmetries act on specific vector spaces. So for instance, if I tell you a given group like SO3, one representation might be 3 times 3 matrix that rotates a vector, right? So this object right here is completely abstract. This is our representation. And I'm going to dig a little bit more into representation theory. So now let's start with this crash course on rep theory. And the thing about the learning curve is that there's always this point where you feel at the beginning that this is really hard, you don't understand anything, then you feel like you get everything, and then you just realize that it's completely impossible. So my goal is to try to get you to about here, so that you feel that you understand enough about representation theory. So again, first let's start with groups, and let's start with the simplest group, which is a discrete group, which is just, again, we already said, it's a set of objects. Here I'm going to talk about the cyclic group of order 2, which we denote as Z2. And it's just a set with 2 objects and an operation. And the way in which we can see how this operation acts on the group elements is via this object right here, which is called the Cayley table. And it's just telling me, I take the identity, combine it with identity, I get this. I take sigma, combine it with identity. I have to get sigma because that's it. That's the action of identity. And I know that everything needs to have an inverse. So sigma has to be its own inverse because I need to be able to get back the identity. And that's it. This is the Cayley table. And it can be built for any discrete group. This doesn't mean that it's going to be efficient, but in principle, you can. Then you can go to more complex. You can have continuous groups, or you can have continuous Lie groups. And the whole point here is like SU2. And maybe for people that work in quantum, this might have appeared in different places, because the way that we understand groups is that now they're continuous, right? I can't just build a Cayley table because I have infinity elements in there. So what we usually do is that we associate to every Lie group a Lie algebra. And studying the Lie algebra is way more natural because this is usually discrete. So for the Lie algebra SU2, we know that it has 3 generators. Now it's an object of 3, it's a set of 3 objects, and there is an operation that connects them. In this case, is going to be the Lie bracket, not to be confused at this point with an anti-commutator, because these are just completely abstract objects. And the fingerprint of a continuous Lie group comes through how the elements in the algebra commute. So take 2 elements, commute them, and you're going to get a linear combination of other elements. So this kind of defines a vector space. And the fingerprint here is going to be given by these coefficients, which are called the structure constants. And again, I've already told you, okay, you need to study continuous Lie groups through their algebras, but how do these 2 guys relate? Well, the Lie group is just the exponentiation of the Lie algebra. So this is just to say groups, we can think about them in discrete flavors and continuous flavors. And at this point, these are just completely abstract objects. E, sigma, G1, G2, G3. I'm not telling you what these guys are at this point. So now, how do we go from abstract groups to the action of vector spaces? And this is what a representation does. It takes an element in the group, and it gives me something in a vector space, acting on a vector space. So for instance, let's set the vector space to be the Hilbert space of a single qubit, so C2. In this case, for instance, I can think about taking my group Z2 and give a representation where I map the E to the identity matrix, 2 times 2 identity matrix, and sigma to the poly matrix X. And it's very easy to check that if I now take the operation to be matrix multiplication, identity times identity is identity, X times identity is X, and the square of any poly matrix gives me the identity. So these two tables match, and now we can see that whenever I have something like a bit flip, and I can either not do anything or flip a bit, this is a representation of Z2. And how do we know this? Because the Cayley tables match. Now I take, for instance, this representation of SU2 given by the poly matrices X, Y, and Z. How do I know that this is a representation of SU2? I just start doing their commutators. Take XY, YZ, ZY, and you will see that these guys satisfy the abstract commutation relationships of the SU2 algebra, where this is, of course, the Levi-Civita symbol, which I forgot to mention before. But this is it. This is why we say, rotations in one spin are generated by XYZ and their representation of SU2. And how do I get rotations on a single qubit? I take elements in this span, so I just linearly combine them and I exponentiate them. So now I know that any unitary that I can apply to a qubit belongs to the group SU2, and it can be written as the exponential of some element in my algebra, right? So this is pretty much what representations teach us. Now, why are representations important? Because this is just the first step of representation theory. The key thing that we're going to use of representation theory is this concept of block diagonalization. So one of the main goals of representation theory is that if I give you a matrix representation R, we want to see if it has invariant subspaces in this vector space. Because again, remember, this is acting on a vector space. So what I want to ask is, are there vectors or subspaces in this vector space such that whenever I act with the group, they stay in there? So I have a subspace that is closed under the action of the group. And this gets translated to being block diagonal. So again, let me remind people, how do we get block diagonal matrices in the language of matrices? So first, if I take a matrix A and the identity, and I do identity tensor A, this is block diagonal. That means that it has invariant subspaces. So again, invariant subspace just equals block diagonal, because if I multiply this big matrix by the 1, 0, 0, 0 vector, I can only get something that has support on 1, 0, 0, 0 and 0, 1, 0, 0. It will never get here, right? And this follows from the block diagonal structure. And we say that if the representation has no invariant subspaces, then it's irreducible or inerrant. So the whole point that we're going to have here is representation theory wants to ask the question, given an element of the group, can I take the representation and write it as a direct sum of something that looks like identities, tensor matrices? And this means that there is some change of basis from the left to the right-hand side. And now I've already told you that this guy right here allows me to do block diagonal. So you see identity times a matrix is block diagonal. But I also have this direct sum right here. So what does this guy do? So remember, if I take a matrix B, and now I do this operation, so I take identity tensor A, something like this, and then I do direct sum with B, it's going to look in this way. So all that this is saying is, can I find a basis where my matrices are going to be block diagonal? And block diagonal gets preserved by direct sum. So this formula that looks very ugly and maybe a little bit intimidating is just asking the question, oh, can I take my matrices and decompose them like this in some basis, right? And why do we care about this? Because then once we have block diagonalizations and we can understand how to take representations, block diagonalize them, but then we also want to think about creating new representations. So for instance, the representations are going to work as the building block. So if I have one representation and another, then their tensor is a representation. And I can do more. I can take this new representation and decompose it into irreps now. So, I could have decomposed R1 into irreps, R2 into irreps, and I can decompose R3 into irreps. And this is not going to be so trivially related to R1, R2. So this is the whole game of representation theory. You have a group, you study its irrep decomposition, you tensor it, then you study the irrep decomposition of the tensor representation, and you just keep going ad infinitum, and this is fun for the whole family. This is all that is going to be interesting for us. Now let's try to ground this. This is very abstract, so let's try to see this in practice. So we've already talked about SU2, and if SU2 sounds too formal, rotations on a single qubit. Right? This is the setting that I'm going to be considering. And, let me just take one element of the group, and let me ask, does it have invariant subspaces? So that means if I start sampling unitaries from the hard random group, am I going to find a basis where these guys are going to decompose into blocks? So here I'm just sampling unitaries, and I'm trying to change bases, and I just can't find any basis. Now, of course, this is heuristics, but we can prove that there aren't really irreducible subspaces. And it's very easy to see that I can go from the 1 state to the 0 state, and hence no invariant subspace. So this is irreducible representation. But what happens now if I take a unitary from SU2 and I tensor it with itself? It might look like this. And you're going to look at me and say, like, hey, Margot, there is no invariant subspaces here either. So what up? Because I told you there exists a basis where this is block diagonal. In particular, if we take this unitary and make a change to the Bell basis, which is given by these 4 guys right here, so we just apply this change of basis to my unitary, it's going to look like this. And now we can see that if I take unitaries and I tensor them with themselves, they do have a block structure where these guys right here and this guy right here is the symmetric and unsymmetric subspaces with respect to the swap. So this is why the Bell basis. So in this case, we would say U tensor 2 is not irreducible. It has a 3 times 3 irrep and a 1 times 1 irrep. And we can actually prove that this guy right here cannot be further decomposed down. So that's it. I think you're all experts in representation theory now. So of course, the question is, how will we ever use this, right? We want to bring this into practice into QML. So, okay, let's go back to geometric quantum machine learning, and let's state that we have agreed that in general, data is going to have symmetries, and that we want to create models that are invariant under those symmetries. So this is the hope of what we would like. So for the examples of the cats, I would like to have a model H. Again, this is my quantum machine learning model, such that if I feed it an image of a cat, or if I feed it an image of a cat that has been acted upon by some representation of an element of an abstract group, now things are hopefully starting to fit in, we want those two labels to be the same. Let me repeat this. I want my label of the cat to be the same as the label of my rotated cat. This is all that we want. So how do we do this? Again, we already defined a setting of supervised learning. Now let's define a setting of what's the model that we're going to use. This is the first inductive bias that we're going to be putting. So I'm going to assume that we have a problem where I'm going to take the data. I'm going to send it through what we call a quantum neural network. But a quantum neural network is nothing more than a parameterized quantum circuit. So I'm going to take my row. I'm going to send it through a parameterized quantum circuit, U of theta, where theta can be discrete parameters that tell me where the gates are placed, or they can be continuous parameters like rotations in a given gate, right? And at the end, I'm going to measure the expectation value of some operator. And my label is going to be obtained by this trace, where here what I'm doing is I'm applying the unitary to the measurement operator. So kind of like Heisenberg picture. So this is all that we need to do. This is my proposition. If I give you a group G and a model of this form, this model is going to be G-invariant if my measurement operator that is rotated by the QNN belongs to the commutant of the group. So I'm introducing a new thing here. I need to define it. What is the commutant? It is the set of all matrices that commute with all the elements in the group. So all that I want is that this guy that I'm measuring to commute with all the representations of the group, of the elements in the group. And it's very trivial to see here that if I act with a symmetry on my data, it's going to translate as applying a unitary to my data. I use cyclical property of the trace. I take the R to this side. Then if my measurement operator commutes, I'm going to send this to this side. And now this is unitary. They're going to cancel each other, and I get a model that respects the label. So this very simple proposition already tells us how to do geometric quantum machine learning. Now let's see it in action. So imagine that I give you this problem. I'm going to give you quantum states, and your goal is to classify them according to their purity. So I'm going to assign label Y0 to all the states that live. Let's say that this is a single qubit problem in the outer shell of the Bloch sphere. So they're pure, right? And I'm going to assign label 1 if they live somewhere inside of the Bloch sphere. They all have the same purity, and it's strictly smaller than 1. And let's say that it's like not exponentially close to 1, so that it's a simpler problem. Now we have to ask the question, what is the symmetry? We need to identify what are the symmetries that are going to preserve the label's purity. It's very easy to see that my symmetry is the unitary group, because I take a quantum state, I rotate it, the purity gets preserved. If I have a state that is pure, rotated somewhere else in the Bloch sphere, is still pure. Completely different state, but still pure. So then we have to find a suitable operator to measure in the commutant of this representation. And again, the commutant, as we will see, depends on representation, which in this case could mean depends on how many copies of my state the model acts on. So let me consider a problem where I only feed my model 1 copy of my quantum state, such that the representation of my element in the group is just the element in the group. This is called the fundamental representation. So here we need to ask the question, how do I find the commutant of the group said otherwise? And this is tensor notation. Maybe this is obvious for people or no. If I take a measurement operator O, which is going to be this box right here, it belongs to the commutant if I act with U dagger, and I get the same operator O. This is equivalent to saying that it belongs to the commutant. So we can just ask the question, what are all the operators that whenever I conjugate them with any possible 2 times 2 unitary, I get themselves? And we're going to see that the only thing that satisfies this property is the identity. There's nothing else. And this arises because this representation is irreducible. I'm not going to get into those details, but you can prove that this is the only thing in there. So the only thing that I can measure is the identity, and nothing commutes to do with the whole unitary group. All that I can do in my model is just trace of rho, which is equal to 1, irrespective of whether my state is pure or mixed. So I cannot solve this. I just cannot build a G-invariant model to classify purity. And I did this just by looking at what the structure of the commutant is. So what happens if I allow my model to act on multiple copies of the data? Say that I just take rho tensor 2 and I feed 2 copies into my data. Now I want to ask the question, what is in the commutant of this representation? Which, again, in tensor notation is, what are the operators such that whenever I conjugate them with U tensor 2 and U tensor 2 dagger, I get themselves? Now we can prove that there's 2 elements in here. The identity, which is I don't do anything, and the swap operator. So the commutant of this representation has 2 elements and any linear combination of them. So for instance, we know that there is a non-trivial classifier here. If I take swap and I measure the trace of rho tensor 2 swap is equal to the trace of rho squared, which is exactly the purity. So we just rediscovered the swap test via representation theory and trying to classify my purity data set, right? And we can again understand this from block diagonalization structure. Here, I had a unitary that had no block structure. The only thing that commutes with this guy is the identity. And my data, it was full. It's a 2 times 2 state. I couldn't do anything. In this case, we already saw that U tensor 2 has this decomposition right here, a 3 times 3 block and a 1 times 1 block. What commutes with this block? Well, I can just put an identity here with some coefficient. what commutes with this block. I can put an identity here with this coefficient. And if I take row tensor 2 and I write it in the poly basis, you're actually going to see that it also decomposes in this block structure. And the information here is precisely the purity. So I just need to access this guy. And I can do this by measuring in the build basis, right? So you can see that identity and swap satisfy this property. So of course, here we could solve this problem because it was very simple. We could just inspect the commutant and solve the whole problem. In general, getting all the commutant is very hard. So what we need is a systematic way to explore and characterize the commutant. And this is the concept of equivariance instead of invariance. And we're going to use this whenever our symmetry groups have too large of a commutants to just look at them and find the solution by inspections like we did here. So now let me go back to this notation of I apply a circuit to U. I'm going to decompose my circuit into layers where each layer is just generated by some rotation by HL. And what we're going to say is that a map is equivariant if it commutes with the action of the circuit. So in this case, acting with the symmetry on my state is the same as acting with the neural network and then the symmetry. So it's just going to commute out. So you can very easily now see that if all the layers are equivariant, I apply my symmetry here. The symmetry is going to commute through all the layers, pop out at the end of the quantum neural network. And if I have an equivariant measurement, again, I'm going to find a model that is invariant. So this is where the concept of equivariance or covariance arises from. So how do we go and build equivariant models? I'm not going to try to tell people all the details, but we have a paper where we have a toolbox for building equivariant quantum neural networks with different approaches. We've studied how they scale, and we've also found ways to do not just equivariant unitaries, but also equivariant channels. And we've characterized different types of equivariant neural networks, like this concept of embeddings or liftings or poolings and projections. We've also characterized them in terms of equivariance and how to construct those guys. And more importantly, we can understand the action of equivariant quantum neural networks and channels via representation theory. And I'm going to go through this very briefly to get to the examples at the end. Because I've already told you that the goal of representation theory is to tell me if my representation admits a form that looks like this. So it's block diagonal. I have some invariant subspaces. This guy is called the multiplicity because it's telling me that this matrix is repeated X number of times. And now we know that we want things in the commutant. We want things that commute with this guy. But if we have this structure, it's very easy to see that anything in the commutant, if I want to commute with something that looks like this, I need to have this form because this is a matrix. It's going to commute with identity. This is identity is going to commute with a matrix. So knowing the form of the block diagonal form of the representation allows us to know the block diagonal form of the commutant. And why is this important? Because now when we take our model and we study what's happening in there, we know that, okay, my symmetry has this block diagonal structure. My quantum neural network, I want it to be equivariant. It's in the commutant. It has this block diagonal structure. My measurement has this block diagonal structure too. So now we start to see and interpret what the model is doing, because my data itself, it doesn't have to be block diagonal, right? Not necessarily. It can be whatever. But because my model just processes information in these blocks and measures in these blocks, I just look at subsets of my initial state, and I can know exactly what is the information that I can access, which are the ones in these blocks, and the information that I cannot access. So this says that equivariant quantum neural networks are a form of generalized Fourier space action. And there's just a subsection of the information of my initial state that my models are going to be able to see. So why is this important? Because if we have classical data, we want to map it into quantum data. We want to make sure that the relevant information gets encoded in parts where my model can see them. Because if my relevant information is out here, it's completely invisible to the model. So geometric quantum machine learning gives us interpretability of what the model is doing. And we now can specifically take a look under the hood and understand what the model is doing. So let me quickly go to the examples to wrap this up. So first, let me consider a case where my group is the symmetric group Sn, where let me just recall that this is a group that permutes n elements. and I just already gave you a group, I need to give a representation. And I'm going to consider the representation that permutes qubits, right? Why do we care about this? Because there's a lot of problems that have permutation symmetry, like learning over sets of elements, anything with graphs, because a graph, doesn't have information associated to the nodes. But whenever we put it in a quantum computer, we need to say, okay, this node is going to be qubit 1, this node is going to be qubit 2. But this information is completely arbitrary. Whenever I see a graph, there is no information on the nodes. So I don't want my choice of this is node 1, this is node 2 to affect the results. So if I permute the nodes, the solution should be the same, right? So anything related to graph, we should use permutation invariant quantum neural networks. And there's a bunch of problems. So how do I build a quantum neural network that is going to be SM equivariant? Well, this is the simplest case right here. Take a circuit, for instance, if I want to do a rotation around the x-axis, I do it on all the qubits with the same parameter. Because now I can very clearly see that this commutes with any permutation. I can take any qubit permutation, it's going to commute right through this unitary. Same with another rotation, and if I want to do entangling gates, I need to do everyone with everyone, which is something that maybe superconducting-based quantum computers cannot do, but atomic traps can do all-to-all interaction. So this is very well suited for those kind of devices. And why do we care about this? Because in this case, we can show that actually imposing symmetries gives us very nice and desirable properties. And this is what we call the holy grail of desirable properties that we can rigorously prove. First, that kind of circuits, in most general cases, is not going to have quantum neural network, irrespective of the depth. So this is telling us, this is an architecture. You can do as many layers as you want. In most cases, of course, there's some caveats here, like your input states have to be well behaved. You will not have barren plateaus, and we can rigorously prove this. Second, this is an architecture that can be rigorously overparameterized with a polynomial number of parameters. And we know that overparameterization is this phase transition in the complexity of solving the problem, where beyond a given number of critical points, training the model becomes much, much easier. Not only that, we can guarantee that this model is going to generalize well from few training points. So no barren plateau, no local minima, because we're in an overparameterized regime, good generalization. This is all that we want. How were we able to prove this? The EREP structure of the problem. I'm definitely not going to get into the details here, but just by looking at the EREP structure, we were able to see that this quantum neural network has so much symmetry that it doesn't really have a lot of degrees of freedom. So again, we can interpret what's going on inside of the model and use that to our advantage. Now, this is theory. Let's go to something practical. Let's consider a problem where we want to build an SU2 equivariant quantum neural network. So again, my group is SU2. The representation is going to be the tensor representation. And this is a symmetry that appears everywhere in condensed matter, like in spin chains. It's also related to entanglement measures. And we want to build a quantum neural network that respects the symmetry. So our work provides ways to what are the pooling layers what are the convolutional layers that we should use? What are the pooling layers? They need to commute with this representation. So we have tools to building this. And we've implemented this for a task of classifying phases of matter. So we're going to take the bond alternating XXX Heisenberg model that kind of looks like this, where the difference is that every time that I have couplings, if I have even, odd, or odd, even, those are going to be alternating values. And the phase diagram looks like this. For different values of delta and j prime over j, I'm going to have 3 phases. In our case, I'm going to stand on delta equals to 1. And as I move j, I go from a trivial phase, from a topologically protected phase. And if delta is equal to 1, you can see that this is going to be SU2 invariant. So I'm going to make the problem even harder. And this is the results by training a just problem-agnostic, hardware-efficient quantum neural network. And why is it so bad? Because I'm only giving it 2 training points. One training point, this x in the trivial phase, one training point, this x on the topological phase. This is an average. This is a representative of an average over many trainings. And you can see that the training accuracy is about like 0.6, so almost as good as a random guess. And these guys are just testing points. And here you can see the ones that I'm misclassifying. If I do the same thing, but I replace the hardware efficient just whatever I'm doing in my quantum circuit by appropriate modules that are SU2 equivariant, I get this guy right here. Now I just misclassify a little bit here with just 2 training points. If I start giving my model more training points, of course, this is going to perform perfectly. And this is slowly going to improve until I'm giving it a bunch of training points and it can do the accurate classification. But again, this has much fewer parameters and much fewer training points to do much better. And we did this just by imposing symmetries and building a circuit appropriately. So let me wrap up and finish and said that geometric quantum machine learning provides a framework to create models that encodes the symmetries of the problem at hand. It can help mitigate some critical issues like barren plateaus, local minima, and bad generalization. And the thing is that there is a lot of work that needs to be done to understand the scope of geometric quantum machine learning. So how do we create embedding schemes? Because this is, for me, one of the main concerns that people want to work with classical machine learning, classical data on quantum machine learning, is that we take classical data that has symmetries, and as soon as we put it in a quantum computer, all of that symmetry information is done, because we're just doing angle encoding or some encoding where it just erases the symmetry information. What happens in generative modeling, GANs, on supervised learning, none of this has been explored yet. And why do I have this image right here? Because I know that there's probably a lot of young, eager, very smart people in the crowd. And this is a new field where, honestly, I feel like everything is a low-hanging fruit. Whatever question you want to ask of, oh, what happens if I put symmetries in here? It's probably not answered. So I feel like we're at the beginning of geometric deep learning in 2016, 2015, where people were just like slapping geometric everywhere and trying to see where it works. But why is this important? Because it's going to help us identify where geometric quantum machine learning will help us and where it will not. Because, of course, geometric quantum machine learning is not the end of the story. It's not going to come here to solve all the problems of quantum machine learning. Of course, if I have very small symmetries, I can expect very small improvements. So it's not going to be as obvious how to solve all the problems, but maybe this is a step forward. So with this, again, obrigado. Thank you very much for listening. And if you have any further questions, I have my email here, and I'd be happy to answer any questions that come up now.
Michael, thank you for your presentation. Very nice. Now we will have time for questions. Michael, can you hear me?
I can. I think I'm not hearing you directly through the. I'm hearing the echo that is coming through the room. So I don't think the mic is feeding into the computer. I can barely hear you.
Here?
Oh, much better. Perfect. Yeah.
Yes, perfect.
Yes.
Okay. Questions? Because this is capturing the audio. We have time for questions. Okay. If you want to make the questions, please come here and ask here. Thiago, please. Just a minute. Se quiser aparecer na câmera, caso contrário.
Hi, thank you for your talk. I was wondering if you can find symmetries that avoid the barren plateaus with the data you know, or it's more general, where you can avoid the barren plateaus with any kind of symmetry.
Right. This is a great question. I would not expect that any symmetry will allow you to avoid barren plateaus. The more symmetry you put into the problem, the more it's going to restrict the expressiveness of the circuit, and the less you have to worry about barren plateaus. But it's not in general. If I have a problem with like C2 symmetry, which is very small, it can still have there. Then you're going to have to impose further restrictions. But you already have a starting point of C2 equivariant quantum QML.
Okay. Thank you.
Questions? Okay, I have one question, Marco. Suppose that you are trying to solve a partial differential equation, and you know the symmetry involved in this problem. Do you believe that this strategy could be useful in this case, solve partial differential equation? I mean, and what is the difference when you compare with physics-inspired neural network? If there is some connection.
It's very much related. I was recently talking to people that wanted to solve some subsurface flow problems on for geology, where they have to solve some fluid transfer equation that was linearized. And we saw that if you impose symmetries in the quantum learning model, it performs a little bit better. And this is very much what people would call like physics informed. For us, this translates to if you're building a parachute quantum circuit that is going to do something, how do you put symmetry in there? Those are the tools that we're giving you. But yeah, geometric quantum machine learning can also be called like physics informed or data informed quantum machine learning. We didn't call it physics because it's based on the data, right? And data is not always physical, but it's the same idea, absolutely. So I would expect some improvement because we have seen it.
Okay, thank you. More questions? Okay, so let's thank Marco again. Okay, Michael, thank you. I hope to see you in the near future, maybe talking with a particular group of quantum machine learning here in this project that they are interested. Thank you again. Sorry, bye.
Absolutely. Send me an email and we'll chat. Thank you very much.
Ciao. Okay.